All right. So let me recall that last time we stopped at the following proposition. So we are talking about.
I'm sorry, you haven't shared the screen.
Oh, yeah, good. Yeah, thank you. Right. Yeah, that's a very good point. In the end, right? Okay, let's see. Right. So now you have the screen share. Thanks a lot. Because I don't see other things on Zoom when I share screen. All right. So we are talking still about that's the last proposition for now from symplectic linear algebra. So we have V omega a symplectic vector space, and we have U and V an isotropic subspace. So let me recall that isotropic means that U is contained in U omega orthogonal. So then the conclusion is that the quotient space U omega quotient by U is symplectic. This symplectic structure omega prime, so it's defined on classes which are vectors in the quotient space, and this is simply omega of AB, where A and B are elements of U omega orthogonal. This is a very simple fact, but this is in some way a prototype of the reduction theorem. So last time we mentioned three big results. One of them was the reduction theorem, and that's basically the linear algebra part of the reduction theorem. That's why I wanted to spend some minutes in the beginning of today's class. So the proof is elementary, but let me still spell it out. First of all, one should convince oneself that omega prime is well defined, right? So, right, I define it using omega. Omega is defined on the space V. We can, of course, restrict it to U omega, but we don't know whether it's well defined, because now we want to define it on the classes in the quotient space. This is very easy. So in fact, omega of A plus U1, B plus U2, where A and B are in U omega, and U1 and U2 are in U, is equal to omega of AB. And this is because U is contained. Why do I say that? Of course, we know that that omega on an element of U omega and on an element of U, it gives 0. So in fact, even I would say probably better. I don't quite know why I didn't wanted to say that. I think more kind of it is just obvious, right? Because all the pairings with the exception of omega of AB, they are manifestly 0, and the pairing omega of U1 U2, it is 0 because U is contained in U omega. So omega prime is well defined, and sometimes one also, I don't know whether you know this terminology, sometimes one says that omega descends to the quotient space. So this is just a language people use. All right, so omega prime is well defined. Now, omega prime is skew-symmetric. So this is really obvious because omega is skew-symmetric. And finally, we need to compute the kernel of omega prime, right? And these are vectors in the quotient space such that omega prime of A plus U, B plus U is 0, right? For all B in U omega orthogonal. But now, by definition, right, this expression, this omega prime, is equal to omega of AB. Well, so it is 0 for all B in U omega prime. U omega. And this means that A belongs to U omega omega, and this is U. And this implies that A plus U is equal to U, and this is equal to 0 in U omega over U. And that's the end of the proof. Maybe one comment. You know, as I said, this is a rather elementary fact. On the other hand, you see, it's somewhat cumbersome how I presented the proof, and I think that's a general feature of linear algebra. I recall, sorry for like bugging you with a personal story. When I started my career as a faculty at the math department, well, when colleagues asked me, what do you want to teach? I said, yeah, linear algebra, because I love linear algebra and I'm not that fond of analysis. So they were very surprised and they said, yeah, sure, yeah, try it. And it turns out that the linear algebra, yes, it's a very, very nice, very clear topic, but it has many simple moves to prove basically any fact. And after 2 moves, typically the audience gets lost. But then after 3 moves, you get lost as well. And so it's these are all simple moves, but it's not always very easy to present them. All right. So as I said, that's a simple but important fact of symplectic linear algebra. We're going to use it later on. But now we go to the new topic, and we're going to talk about symplectic manifolds. I'm not sure, probably many of you know a lot about that stuff, or some of you perhaps don't. So I will be presenting it with some details, more or less from scratch, but some things tell me if they're too detailed, or some things are not enough, there is not enough details. So the definition that we already seen last time, so M, a smooth manifold, and omega, a 2-form on M, is a symplectic manifold if the following 2 conditions are satisfied. So the first condition, omega is non-degenerate. So that's a condition similar to the one that we saw for symplectic vector spaces. And we're going to discuss it in great detail in a couple of minutes from now. And the second condition is that the Durand differential of omega is 0. So that we will also come to discuss it. So let me first discuss the condition number 1. Right, maybe it's good to start with a discussion in a local chart. So we have some local coordinates, x1, xn, and a two-form omega can be written. Again, you know, there is this convention with 1/2, which is not very important. So can be written in the following form. Right? Here, omega ij is a matrix, which in principle depends on coordinates. And conventionally, we say that this matrix is skew-symmetric. In principle, if you want, you can add a symmetric part, but it will not contribute in omega because the wedge product is skew-symmetric. So conventionally, omega ij is skew-symmetric. So now the condition is that the determinant of this matrix is non-zero for all points x. Yeah, is there a question? Right.
It's the same that each like tangent vector space is symplectic vector space.
Sure,
yes.
Sure, yeah, you're right. I'll tell. I kind of yes, probably on the next slide that condition will also show. But yeah, of course you're right. That's the same. Now another way to express it. If you take L, remember we were doing it last time in the case of a vector space. We take the nth power of omega and conventionally divided by n factorial. Then this is non-zero. So that's the same condition. We saw it locally last time in symplectic linear algebra, and here this condition is basically the same. Doesn't matter whether you do it on a manifold or on a vector space. So there are consequences of this fact, right? Since you have a form, there is one small thing that I think I should change. Let me say here 2n instead of n, right? We know that those symplectic manifolds should be of even dimension. Let me call the dimension 2n, and then the power of omega will be n, right? Otherwise, what I'm saying does not make sense. So this is a non-vanishing differential form of degree 2n, and there are topological consequences of it. So this means that M is orientable. So you can introduce the positive frames with respect to which this form, this top degree form, would be positive. So this L, this is called the Liouville form. Liouville form is a volume form. And in case when M is compact, what you can do, you can define an invariant of your symplectic manifold. So, and this will be just an integral over M of L, right? So this is called symplectic volume.
Anton, there is just a question in the chat. Somebody asks, why is it n and not 2n in the definition of L? So maybe just in case there is more than one person who wants to hear this, you can just repeat the explanation.
Yeah. Thanks a lot. So, I've now decided that the manifold is of dimension 2n, and then omega is a two form. So if you consider its nth power, this would be a form of degree 2n. And if 2n is the dimension of the manifold, that's a form of top degree, of the maximum possible degree. Maybe one more comment. I don't know whether everybody is fluent with this, whatever, orientable stuff, right? Like more like in the topology direction. if not, maybe in the first approximation, don't pay attention or ask me a question. So I will perhaps now mention one more thing where I'm not completely sure whether everybody is fluent with the language. I will make some comments on that, but just in case, don't hesitate to ask.
Yeah, I'm sorry. Actually, I have one little question. So actually, M is not just orientable. It is actually oriented already. So we have.
Yes, that's right. Of course, there is no contradiction. Orientable and oriented. Let me write it here. Okay, thank you. Yes, it is also oriented by the Liouville form.
Yeah, as canonical orientation. Yes.
Yeah. Yes, absolutely agreed. Yeah, thank you. Yes, it is oriented so that the symplectic volumes are positive, right? If you change the orientation, then the volumes become negative, but we choose the orientation such that symplectic volumes are always positive. That's right.
Anton, there are so many questions in chat, and I don't know whether maybe we should, it's up to you, you should decide, but I don't know whether you want to encourage people really to ask aloud instead of putting it in the chat.
Yeah.
I really think
that's a good idea. Yeah. Just of course we'll see if we drown in questions.
Yes, exactly.
But I mean, yeah. Please unmute yourself and ask.
Please, all of you, you need to understand that Anton doesn't see these questions, and we're getting answers as well. Very good answers, and that's also great. But it's not a perfect situation because we want to try to reproduce. We want to try to reproduce the real live interaction.
No, but I mean, if I mean, it's also very good if there are good answers on the chat. So no worries. I think we should use all the channels.
Yeah.
But I mean, maybe if there are some questions which are unanswered on the chat, unmute yourself and don't hesitate to ask. Oh, maybe I can actually see them. Oh, maybe you know. Wait. I can see them. Yeah. Right. So sorry. I think actually I now see the chat. Yeah. Right. Okay. So I think some of those questions I will answer on the next slides. So okay. Let's wait and see. So. Now let me recall, or let me tell you one thing. I'm not sure again whether people are fluent with it. Let's talk about the second homology of M with values in reals. Of course, there are many homology theories. I don't know whether you know any of them, but in particular, right, there is Durham homology theory, where this group is simply the following thing. So these are two forms which are closed, divided by the space of two forms which are exact. That is, they are Durham differentials of one forms. Right, so that's the definition of the Durham homology group, but then it is also equal to various other definitions of homology groups, but that's maybe not that interesting for us. So now the fact is, that's the consequence of the definition, that again, if M is compact, then the class of omega, right? Omega is a closed two form, so it defines some class in that quotient. So it defines some class in the real Durham homology, and this class is necessarily non-zero. So why is that? So that's because of the following. Let's prove it by absurd. So assume the class is actually zero, meaning that omega is the alpha. So then what happens is the following. So you compute the volume of m omega, and this is equal to the integral over m, 1 over n factorial, d alpha to the n. And if I continue the calculation here, this is equal to 1 over n factorial d of alpha, d alpha to the power n minus 1, right? Because the Durand differential squares to 0, so that's just a correct calculation. And so we have an integral over m of a total derivative. Then by the Stokes formula that you probably know, right? M has no boundary, no nothing. It's a compact manifold. So this integral is 0. But we said that L is a volume form, right? So by some standard calculus, if you take any small ball, you already get some positive answer, and you get a strictly positive answer for any small ball. So this is in contradiction. This is in contradiction with this 0 result. So this cannot happen that omega is equal to d alpha, and this means that it should be non-vanishing cohomology class. And then this implies the following interesting consequence, that in particular H2 of MR cannot be 0. So you cannot have a vanishing second cohomology group. Again, I don't know to what extent. For now, like if you know nothing about cohomology, just take it as an information. If you know something about cohomology, right, it's already an interesting fact that you always, for compact, at least for compact manifolds, you always need this H2 non-zero. We're gonna return to it later on in the course, but now maybe just to say that this already excludes many possible examples. For now, we knew that symplectic manifolds must be even dimensional, but apparently not all even dimensional manifolds are good. For instance, if you take a sphere S4, or if you take a Cartesian product of a circle and a sphere S3, so this cannot be symplectic, because it turns out they don't have non-vanishing H2. Again, if you know what is H2, then you would probably know that those spaces have vanishing H2. If not, let's say for some simple spaces, we can look it up in some table, and the table would tell us, okay, the H2 is 0 for those spaces. So no symplectic structure. Okay, so this was a little dive into topology. These are very, very simple things. Of course, people doing symplectic topology, they dive much, much deeper into the question, but at least some small things which are useful for us. So now let me get back to some more elementary stuff. And already someone mentioned, so if the manifold is symplectic, then each tangent space, together with the value of the of the symplectic form at the point M, is a symplectic vector space. So maybe just to stress it. So we have two conditions. The condition 1 with non-degeneracy, and condition 2, the Durand differential is equal to 0. So the condition 1 is actually local. This is a point by point. We verified, and the consequences are point by point. Of course, in the condition 2, we take derivatives, and so here it tells us how the two form behaves when we move from one point to the other. But condition 1, this is simply verified for each point. So here there are further observations. So you can again remember we had this musical map omega flat, so we can take it at each point, and following our linear algebra discussions, right, it induces an isomorphism at each point from the tangent space to the cotangent space. Now we can actually do it at all points at once. This will define for us a map or omega m. So there was a question of what is omega m. That's the value of the two form at the point m, right? So so this is the two form, right? And you can restrict it to one point, and this will be as bilinear skew-symmetric bilinear map on the tangent space at that point. Maybe now you will see it a little bit better with this omega flat and with the further discussion. So we're getting a map from vector fields to one forms. And these are one forms. And how does it work in a chart, in a particular coordinate chart? So here we have a vector field V, which is a sum to n vi of x d over dxi. And where is it mapped? It's mapped to the following gadget, vi of x omega ij of x dxj. Now maybe there is a test question. Remember last time we were discussing those 1/2 factors and so on. So remember in the definition of omega, I have a 1/2 in front of the sum. Maybe a test question for you. What happened with this 1/2? Is it a correct formula, or have I missed 1/2, or what happens? If you know the answer, just put it on the chart or unmute yourself and tell everybody what happens. So what happened with 1/2? Right, I leave it as an open question, this 1/2 mystery.
Excuse me, we have written 1/2 when there was two forms, like dx times di has a coefficient 1/2, but dx itself hasn't any coefficients because it's like 1 factorial in denominators, because it's kind of like усреднение.
Wait, but what? That's the formula for omega, right? Okay, so that's the formula for omega, and it has 1/2 in front of it. Now I put in my vector field in it, and now there is no 1/2. What? So could you spell?
It's just because there was like omega ij and minus omega ji, and they added up.
I would, okay, maybe that's one way to say it, but I would put it that way, that you should put this vector field in dxi, and then minus you should put it in dxj. So there will be two terms, but they will turn out to be the same. And that's where 1/2 goes, right? You have two terms. So this is a factor of 2, and it cancels the factor of 1/2, I think. So I invite you, just if of course, probably many of you are very, very fluent with it, but if not, just check that this is indeed the case. So dxi dxj, this is dxi tensor dxj minus, maybe I just write it. So this is dxi tensor dxj minus dxj tensor dxi, and you substitute your vector field in the first determinant. Yeah, there is a question on the chat. Yeah, there is a determinant. Right. Non-zero for any x. Yes. So you substitute your V either here or there, and this gives two terms. Those two terms are actually the same, and that's how it goes. Okay, very good. So
Excuse me,
yeah.
I have a question about previously we proved that the second homology do not vanish. Doesn't the same proof work in case of a non-compact manifold? I think we can take integrals over compact submanifolds, I suppose.
No, it doesn't work. First of all, we'll see. One can relatively easily give counterexamples, right? But okay, that's of course not a real explanation. But you know, what's what's your opinion, right? So what goes? I think what goes wrong is this equality, and what's going wrong with this equality, right? Up to now, everything is fine, right? You assume your form is exact. Okay, good. Of course, already something goes wrong here because
well, I mean, I thought we can take the integral over a compact submanifold.
Okay, but then right here that's very good. So we choose a submanifold. This submanifold is symplectic. However, typically it's going to have a boundary.
Oh, I see.
So in the Stokes formula, you're gonna instead of this right-hand side, you will have some integral over dm or blah blah blah, and then there is no contradiction. Yeah, this integral may be a positive number, which represents the volume of your compact submanifold.
Yep, I see. Thank you.
Yeah. Okay.
Excuse me, may I ask a question?
Sure.
Does non-degeneracy of our two-form omega imply that its nth power is not degenerate everywhere?
Yeah. Yes. Yeah. It's equivalent. Maybe think about it. That's more or less what we. That's basically a linear algebra question, right? Because you do it point by point. So what we saw last time, that's the assertion in one direction. If omega is non-degenerate, then it has this normal form, right? What we had last time, E1 wedge F1 or X1 wedge Y1 and so on. And then we take the nth power, which is by inspection see that it's non-vanishing. But I think in the other direction that would be also easy to prove, because if omega has a kernel, then all its powers, they also have a kernel. And then if you take the nth power, then it will be vanishing on some of the vectors. So it cannot be a volume form. So these are, I think these are equivalent. And this is a linear algebra question. And right. Okay.
Thank you.
Thank you. So now what I wanted to tell you, again, I don't quite know how fluent you are with this material. I'll tell you something, and perhaps you tell me whether you know all that. So so I want to remind you of the Cartan calculus. So maybe more precisely, suppose that on any manifold, now it doesn't matter, symplectic, not symplectic. So suppose we have a vector field. So then there are two operations on forms that you can construct from each vector field. And the first operation is called contraction. And there are different notations for it. I use this notation iota of V, but in the literature, there are other notations as well. And what this operation does, it decreases the degrees of forms by 1. And how does it act? Well, suppose you take a K form alpha, you should produce a K minus 1 form. And what you do simply in the first, as a first vector, you put your vector field V, and you leave all the other entries vacant. So here would be K minus 1 slots. So this will be a K minus 1 form. So have you seen such operations before?
Yes.
We called it partial applying or something like this.
Okay, perfect. So then it will be fast. So now the second operation is more involved. So from a vector field, you can produce an ordinary differential equation, which looks like that. Again, I write it in a local chart, right? And then let's assume that at least for some short time, this differential equation integrates. So of course, you know, integration of ODEs, that's a complicated question, but let's assume that for at least for short time, you can associate trajectories to this differential equation. So, and then this would define for us maps phi t, which maps x of 0 to x of t. So here you have some initial condition, and after time t, you arrive at the point x of t. So sometimes this is also denoted as an exponential of tv. Of course, this is just a notation. Here, well, I mean, it's an exponential in the group of diffeomorphisms, so something complicated. But for us, what is important is that this xi of t is xi of 0 plus t vi of x of 0 plus O of t squared. So everything is smooth. If the solution exists, the solution would be of this form. So now there is a gadget which is called the Lie derivative. Again, I think you probably heard about it, or maybe not. So the Lie derivative maps the forms of degree k to the forms of degree k. And what it does is the following. Let me write the formula, and then I compute it concretely in an example, so you will see how it works. So you take what is called the pullback of your form under this map phi t. You differentiate over t and compute it at t equals 0. So for now, if you don't understand the notation, don't pay attention, but I'll now compute an example, and I hope it will become clear what happens. And then there will be an exercise with a slightly more involved example in the next problem set. Here, I must say, I'm always confused with signs in differential geometry. You know, signs is a complicated matter, and maybe the experts can later give me an opinion. I know that in many sources, this sign, people prefer to put a minus, so they prefer to run it in the opposite direction. So in preparing this lecture for several days, I tried to figure out my signs. Yeah, I'll let you judge whether it worked or not. So my example will be, I will run those operations on functions. Well, functions, these are differential forms of degree 0. Now, first of all, a nice observation, if you compute a contraction on a function, then you simply get 0, right? Because a function is a 0-degree form. There is nowhere to substitute your vector field. So like, okay, this settles settles the matter. Now, a more advanced exercise. I want to compute LV of F. And in fact, it will turn out this is something that you know already. So I computed at the point X. So this means,
This is just V of F.
sorry?
That's just V of F, I guess.
Yeah, that will be just V of F. But of course, for differential forms, as I say, there will be an exercise in the problem set where I ask you to compute it for, say, 1 forms. What should I do? I should take phi t star F. So this will be again at the point X, and I should compute the derivative at t equals 0. So what does it mean? This means d over dt f of phi t of x at t equals 0. And this is d over dt f. And here I write it like this: x plus tv of x plus o of t squared at t equals 0. And well, as you already noticed, well, I take a derivative. So this is d phi over dxi times vi of x. Right. And of course, we know it also as v of f. That's right. Finally, let me do one more calculation and end up with the main theorem of the Cartan calculus. So I will also do iota of v applied to the Durand differential of f. So this is iota of v, sum over I, df over dxi, dxi. And this is equal to the sum over I, df over dxi. So note that these two things coincide. Now, how is it? Many people probably know what's the main theorem of Cartan calculus, or not necessarily?
Yeah, it's Cartan identity for Lie derivative, like e dx plus dix.
Yeah. So yeah. So the name, the usual name for it is a Cartan magic formula or Cartan magic. And yeah, you're right. It says that L of V is D composed with iota V plus iota V composed with D. So that's a very, very important formula. So that's good that you know it already. So notice that we actually proved it for functions, for the echelon functions, right? Because d iota v of f is 0, lv of f is this answer, and iota d of f is that answer, and they are the same. So we actually proved it on functions. And just as an exercise, in the next problem set, I'm asking you to reprove it for 1 forms, just as an exercise. But it's great that you already heard about or used that formula. So now we want to use the Cartan calculus in our symplectic geometry story. And in fact, we'll be using it a lot. That's why I thought maybe it's a good idea to spend a couple of slides on it. So the next definition is symplectic vector fields. Now assume that our manifold is symplectic. So then there will be various kinds of vector fields that we can define on it. And we say that V is a symplectic vector field. if the Lie derivative under V of omega is 0. Right? So that's a very simple condition. Well, a very short proposition. So V is symplectic. If and only if iota V omega is closed. Now, well, also a one-line proof. So LV omega is d iota V omega plus iota V d omega. But now this is 0 because our two form is symplectic. So only the first term remains. And the first term is the Durand differential of the one form iota V omega. So this means if the left-hand side is 0, the right-hand side is 0, and the other way around. And this is just a condition of being closed. If this is 0, and this is a condition of being symplectic. So they're just the same condition. Now,
excuse me. So again, the statement is that given a closed form, it is symplectic if and only if the corresponding if and only if, what, by the way, are we given a
you want to run it, right? You want to run it in the other, so it's slightly more complicated, right? But you want to run it in the other direction. You want to take a closed one form, right? And then produce from it a vector field, and then it will be symplectic. This is also true, yes. Because this omega, right? The omega flat is an isomorphism. So you can run it, you can invert it. So map one forms to vector fields. We'll do it now in a slightly more restricted situation.
May I ask a question?
Sure.
How many symplectic fields are there for the particular symplectic form?
Right. I think, yeah. Okay. Let me add that remark. So this develops the previous question, right? In fact, we know all of them, right? We have omega flat, which maps vector fields to one forms, and we know that this is that locally this is an isomorphism. So let's assume that M is compact. So then I think the inverse will also be smooth and bounded, right? We may, like, since we're working on a manifold, maybe we can be asking what happens if you go far away. What if, let's say, we introduce some norm for this map? What if this norm goes to 0 somewhere? But if we are on a compact manifold, right, on a compact manifold, everything has a minimum. And if the norm is positive, it's going to have a minimum, and we can smoothly invert it, right? So if M is compact, then I can construct omega flat inverse. It will be mapping one forms to vector fields. And here I can just take, as was suggested in the previous question, I take any closed one form, I obtain a vector field, and it will be symplectic, right? So, so here closed will be mapped to symplectic. Then the short answer is there are lots of them. Like any closed one form produces for you a symplectic vector field. So many. Of course, in some way, that's a much smaller number than all the vector fields, because still among all the one forms, the closed ones, right, we have a complicated condition to impose, but otherwise lots and lots of symplectic vector fields. Right.
Do you mean that that we take one form and get a symplectic field, but for one form from a particular one form, there is one corresponding
Yes.
symplectic vector field?
Yes. So on the chart, you're saying that the compactness is not needed. You know, yeah, let's say in some way you're right. Depends on what will be the properties of your vector field. Of course, locally you can always invert. This is true. But I mean, if you have some infinities, maybe your vector fields will be growing like mad at your infinity, whatever. Right. Okay. Good. So the next question I wanted to discuss are Hamiltonian vector fields. So again, a definition. Suppose we have a symplectic vector field. Then we say that it is Hamiltonian if there is a function h on M such that iota v of omega is equal to dh. Right? So maybe to rephrase it, right? We're now saying that this one form, we know that if our vector field is symplectic, it should be closed. But now we want it to be exact. Right. Okay.
Excuse me, I'm still a bit confused about the previous definition.
Sure.
Of a symplectic vector field. Do we assume the manifold to be symplectic in first place?
Yes, yes, absolutely. Yes.
And so then I don't really understand what was said about omega flat. Because I mean, we have a, oh, here is, oh yeah, I understood. Because omega is a two form, but not a one form. Yep, I understand now.
Yeah, we assume M to be symplectic. So omega is the symplectic form on M, and omega flat, remember, is that mapping vector fields to one forms.
Yep, I see. And so the definition of a symplectic vector field is basically that the image under this isomorphism, the image of the subset of closed forms under this isomorphism.
I mean, as you like, you can take it as a definition, since the proposition is one line, the proof is one line, but the official definition is that the vector field preserves the symplectic structure. And this means that, remember the definition in Cartan calculus of this L, right? You take a flow of your vector field and you differentiate the form along that flow. So we're saying that the flow of V, at least at the point t equals 0, it preserves the two form. So the derivative of the two form along the flow is 0. So that's this condition L of V omega is equal to 0. So you run,
yes, I see now.
You run your vector field and the two form does not change. Basically, symplectic vector fields, these are infinitesimal symmetries of our symplectic structure. If we can integrate them, I mean, assuming that a vector field integrates to a diffeomorphism, then those diffeomorphisms will be real symmetries, will be automorphisms of a symplectic structure. So you move your manifold in some way, and you look again at the two form, and it turns out that it's the same. It didn't change. Right. Okay. Okay. So maybe a couple of remarks about this definition. So the first remark, if we assume that M is connected, so then for a given vector field, H is unique up to an additive constant. And again, the proof is elementary. Suppose that you have two different H's. In fact, you know what? Again, I already declared I'm very bad with signs. So let's put here minus sign. I think I need it somewhere to get good physics formulas. Maybe even today, we'll see. So suppose we have two different functions, h and h prime. So they are dh is equal to iota v omega with plus or minus sign for both of them. But then this means that d of h minus h prime is 0. And this means that h minus h prime is a constant if the manifold is connected, right? So here you need connectedness, but typically we always work with connected manifolds. Now, in the other direction, so we have this omega flat of v is equal to minus dh, and then we decided that we can invert omega b, and this means that for a given h, there is a unique v which satisfies this condition. So the terminology is that, or at least sometimes in physics, right? People use the terminology that h is a Hamiltonian function or Hamiltonian, and VH is the corresponding Hamiltonian vector field. So now I realize that something really bad happened, because in my preparations, so I didn't preserve the order of pages. And in fact, before diving into all the story of symplectic vector fields and Hamiltonian vector fields, I wanted to give you lots of simple, almost trivial examples. But fortunately, we still have around 20 minutes, and we'll now look at the examples, very simple examples of symplectic manifolds, and then also see how those Hamiltonian vector fields, how that story plays out. So, examples. So the first example, which is the most standard one, m is equal to r to the power 2n, and it's equipped with coordinates q1, qn, p1, pn, with also traditional names, and the standard symplectic structure is a sum from 1 to n, dpi wedge dqi. I think actually some dissident people, they write dqi wedge dpi, right? That's a big question. I was recently teaching a course on introduction into symplectic geometry and mechanics, and she wanted to use DQI, wedge DPI. So that was very, very hard how to reconcile our conventions. But you know, that's the standard, at least one of the standard choices. It is obvious that this two form is closed. That's because it consists of wedge products of closed one forms. If you write the corresponding matrix, so we can write it in the block form. So the blocks are n by n, and here would be 0, 0, and if I'm not mistaken, it will be the unit matrix and minus the unit matrix. This ordering of coordinates, first q's and then p's. So it is also obviously non-degenerate. It doesn't have a kernel. So just by inspection. Now, note that also if you take any open subset, this will also be a symplectic manifold, right? Just because all those facts are local closedness of the form, non-degeneracy is even point by point. So you already mentioned another example that I wanted to explain. So sometimes it is more convenient to use complex coordinates. However, in our business for now, sometimes perhaps we'll consider complex symplectic manifolds, but for now we're going to use Cn as a manifold over R. So this actually means that, to be honest, we identify it with R to n, and we are using, in addition to holomorphic coordinates, anti-holomorphic coordinates. So now it is basically R to n, because we can say that Zi is Qi plus, maybe for now I write the square root of -1 for imaginary unit, Pi, and Zi bar is Qi minus square root of -1 Pi.
Excuse me, I never understood this, and maybe you can explain how we can call this Z1 and Z1 bar coordinates when it's not like something like independent things. Because like if we have Pi and Qi, we can like set arbitrary numbers. And if we like fix Z1, then Z1 bar is already like given to us.
No, but you see, like you will see now. We assume now, of course, Z and Z bar are not independent in this picture. I mean, it depends what you're doing, but what I'm doing here. So Z and Z bar, you're right. They are not independent. They are related to each other by complex conjugation, right? But then basically what you're doing, you are viewing functions of Z and Z bar as functions of Q and P. But Q and P are independent coordinates. So for this reason, you can also express everything, for instance, all the derivatives, all the forms with respect to Q and P as derivatives and forms using Z and Z bar. You can also think about it in the following way. Suppose you have a complex space with two n coordinates, Z and Z bar, but you're only living on the real subspace where Z is equal to Z bar. So perhaps you will see from the next formula. So I rewrite omega standard in the following way. It's 1 over 2i, sum now from 1 to n, dzi wedge dzi bar. And now what I mean is the following. If I substitute the expressions above for zi and zi bar, I will reproduce my standard two form, which is real, and which is the sum of dpi wedge dqi, right? So in principle, you can think of this omega standard DZI bar as a holomorphic two form on C to the power 2n with coordinates Z and Z bar. But then when you restrict it to this real submanifold where Z is equal to Z bar, you get the two form that I started with. For now, is it a good explanation? Or not convincing?
So, like, I have heard something like this before. I just maybe want motivation why Z is not enough, and we need to consider Z bar 2 for describe two numbers P and Q. When Z
you will
is
see. Or just let's say for now it's just a matter of convenience. Yeah, for now it's just a matter of convenience. Yeah, you're right. If I'm consistent, there is another comment on the chart that I should write a square root of -1 instead of I in this set of formulas. Yeah, you're right. It's but you will see sometimes it is somewhat more convenient to do it. But the meaning is like in the example 1. Example 2 is no different from example 1. Some things will be more convenient to present in that language, but in content, there is no change. Now let's do some change.
So my question can be formulated as what is, for example, DZI bar? Like this.
It's dqi minus the square root of -1 dpi.
Is this definition?
Yeah,
is this okay.
Absolutely. Yes, absolutely. Right.
It's simply differential of a complex function.
Yeah. So Zi and Zi bar, that's also a very good point. This is simply complex valued functions. So our manifold is a real manifold, but I'm allowed to consider complex valued functions. Why not?
Okay, thank you.
Okay, so example number 3, also very important in practice. So we consider R to the n times the n-dimensional real torus, which is simply a product of n copies of the circle. And maybe just for now, there are many names for the corresponding coordinates. Let me call the elements of Rn by capital I's and angles on the tori on the circles by thetas. And well, the standard 2 form is still the same. You know, this basically doesn't change. So here I just changed the topology of, I could have thought that I had R to n, which was a product of Rn times Rn. And now I changed the topology on one of the factors. Instead of real lines, I took circles. It still works. And of course, here again, I can also take some open subset of Rn times Tn. So that's what often happens. And there is a special name for this type of coordinates, which comes from mechanics. So people say that these are action angle coordinates. So angles, there is no secret why, actions, whatever, for some historical or mechanical reasons. But when you hear action angle, this means exactly this, that locally your manifold looks like that. Finally, an example that some of you already mentioned in the chart. Suppose that M is an orientable, or if you wish, oriented to the manifold. And we can choose omega to be any volume, or maybe in this case, it's better to say area form. So maybe here 2 sub-examples. Probably the simplest one, we take M to be a 2 torus, which is S1 cross S1. and let's say I call the two angles phi and psi, and one possible two form would be d phi h d psi. But of course, you can multiply by any positive function, right? Here, the closeness condition, what's the advantage? The closeness condition in dimension 2 does not apply, because when you take a Durand differential over two form, it should be three form. There are no three forms or on two manifolds. So therefore, everything which is in degree 2 is closed. And this must be non-zero. So here you get lots of symplectic forms for free. Perhaps another famous example that we briefly mentioned last time already. So M is a sphere in R3. So it's a two sphere of radius R. And for symplectic reasons or for historic reasons, we usually take omega R to be 1 over R times the Euclidean area form. But of course, this is just a convention. You can put any number. Actually, you can also put any positive function. So there will be again many symplectic forms. This is one canonical choice, and we probably get back to it in further discussions. So there are some questions.
I have a stupid question also. I think it's fast. Is d theta I a closed form? One
Yes.
example 3.
Yes, d theta I is a closed form, but this is not an exact form, right? Because
Yes. So now the question is, like, we can take t to the power 4, like with all sums like this, like using same thing, but with t2 multiplied by t2. But this shouldn't be like
sorry.
symplectic, because second cohomology is 0, or not. Is t to the power 4 symplectic manifold?
For compact manifolds. The claim was only.
But maybe let's. I'm not sure whether it answers your question. But if you look at 4 prime, right? This is S1 cross S1, right? And there the two form is d phi wedge d psi, right? I'm suggesting that two form. So this is a compact manifold, and so we should check whether H2 is non-zero. In fact, the H2 is non-zero, and this omega d phi wedge d psi is a generator of H2 over reals. So this is So it's kind of up to now. It's consistent.
So short questions: can we multiply 4 circles, not 2, and use same form?
Sure. Yeah, absolutely. You can. Yeah.
Okay.
Maybe, yeah. You can of course take tori of any dimension. Right?
But only on even dimension.
Yeah, right. Or for even dimensions, you would be able to construct lots of symplectic structures. For instance, if you have a torus of dimension 4, you would have d phi 1 wedge d phi 2 plus d phi 3 wedge d phi 4. That would be symplectic. You can play with it and construct many other symplectic structures. Sure, absolutely.
Okay, thank you.
Okay, good. So maybe the last thing I want to show you today is an example of how Hamiltonian vector fields play out in example 1. And you will have in exercises 2 more examples, which are a lot more complicated, of symplectic manifolds, the cotangent bundles, and also projective spaces. I'm not sure, there are many questions on the chart, but maybe you can speak up, because I have 2 examples, both T2 and S2, right? For prime is T2 and for double prime is S2. So maybe I don't quite understand the questions. So Hamiltonian vector fields on R to N, omega standard. Right, so maybe I just give you an answer, right? To so that's a simple exercise to check that if you take a function h, then the corresponding VH would have the following form. This will be sum over I. So the partial derivative with respect to pi divided dqi minus dh over dqi over dpi, right? So that's just an exercise, right? And to see that this follows from u to the omega is equal to minus dh, and that's why I need that minus sign, because now we'll have some nice physics formulas. So I don't quite know whether you had a classical mechanics course, or probably perhaps you saw those formulas many times, or maybe not at all. First of all, what is the corresponding ODE? So the ODE corresponding to that vector field is dqi over dt is equal to dh over dpi, and dpi over dt is minus dh over dqi, and this is called Hamiltonian mechanics, or canonical equations in Hamiltonian mechanics. If furthermore you take h to be of that form, 1 over 2m sum over I pi square plus some function of q's, so then the following thing happens. Your equations look as follows: dqi over dt is pi over m, dpi over dt is equal to minus dv over dqi, and this in turn implies d2qi over dt square is minus 1 over m dv over dqi, and that's the thing that we know from high school as a Newton's law. Right, this is just a reminder that this stuff in principle, right, for some particular cases, right, you're right, derivatives in local coordinates is my vector field. Yeah, you're right. Basically, yeah, maybe that I should say. So this is equal to v or maybe v of qi.
He was just answering a previous question, I think.
Yeah, right. Okay. So I think that's it for today. So what we're going to do next time, we'll see more examples of symplectic manifolds, and I'll start talking about Lie groups, and we'll produce. I'll try to teach you some kind of some kind of maybe not completely foolproof, but I mean shorthand way of dealing with differential calculus on Lie groups and on related spaces, and will produce interesting and non-trivial examples of symplectic structures related to Lie groups. In the meantime, is it okay if I stop sharing at least for a moment? And I want to put, maybe I can put in the chat just like that. I would like to put the current version of the next exercise sheet. Is it? No, sorry. Right.
Okay. So today will be seminar in a few minutes, yeah?
Yeah. I think maybe Jan, you can say more about
Sorry,
it.
I have 3 little comments, maybe off topic, but about the content of the lecture.
Yeah. Okay. Perfect. Yeah. Go ahead. I'm just trying to put this exercise. Yeah. Tell me.
Yeah. The first one is about second cohomology. I guess maybe it's worth mentioning that this implies that all even dimensional cohomology is not 0 as well.
Yes, that's that's true, because that's right, because all the you're right, because all this other even cohomology. Sorry, just a sec. I'll answer this question, but you're right. All the even cohomology groups are non-zero. That's right. Because the powers of the symplectic form, right? They. Ian, could you put in the chat the file, because I'm somehow my machine refuses to cooperate on that. Ian?
Sorry, which file am I putting in?
Symplectic X2 PDF.
Okay, but I mean, yeah, but I only got it about, I think it will be on the site, by the way.
It will be on the site, but I think it might be kind of useful to have it already now in the chat.
I don't know even if I have it available, by the way. I had it about 10 minutes before the class. I'll have a look if I have it.
Perfect place for this like sheets is Telegram chat, because
it will be fine. Everything will go in the site, in the website.
Yeah. So, but you're right about the previous comment. Yeah, that's right. So omega in H2 is not 0, and then we know that omega to the n, right, in H to n is also non-zero, but this means that omega k is non-zero for all k between 1 and n, and these are exactly all the even degrees that we have. So you're right, all the even cohomology groups, they need to be non-zero, absolutely. But you said there were 3 comments. That was the first one, I assume?
Yeah, the second one is about examples. I'm sorry, I don't remember the numbering, but could you please just show me them? Yeah, about the first and third examples. Yeah, I guess this is just the case of cotangent bundle. Yeah, the claim that cotangent bundle over any smooth manifold is a symplectic manifold, and this is just particular examples of
this is right, and the cotangent bundle example is in the next problem set. Yeah, you're right.
Yeah, and the last, well, this kind of counterexample of yeah, I just thought about that, but the example of S2 cross S4 is, I guess, a good example of non-symplectic manifolds where all even dimensional cohomology is not 0.
Right.
Is it non-symplectic? Can we just take like dphi times deep C plus functions for S4? S4 is like non-symplectic. Okay.
Yeah, you're probably right, but of course I would yeah, right. Yes, you're probably right. I think S2 cross S4 cannot be symplectic, right? Because
Yes,
right.
just because there is no these two form squared zero.
Right. That's correct. Yes. Yeah, that's right. Thanks a lot. So you're saying that. Yeah.
Excuse me, can I have a question? Can I ask you a question?
Sure.
Maybe it's elementary question, but is there any certain relationship between complex manifolds and symplectic manifolds? For example, can every complex manifold get a symplectic structure or vice versa?
Oh,
I think the converse is not true by the third example you wrote. For example, R times T1 is not a complex manifold, but the other way, is that true?
I know. Let's say part of the answer to your question is standard wisdom. For part of it, probably I should look it up. That's probably also standard. But so this is not true that every symplectic manifold has a complex structure. I think that there are maybe relatively tricky or maybe even not tricky counterexamples. But this is true that every symplectic manifold has an almost complex structure. Almost complex structure, this means that you have at a point you have a complex structure, but they don't integrate into a real into a true complex structure of a manifold. And those almost complex structures, this is something which is used in general. So and that perhaps we're gonna discuss later on in the course. There is a class of symplectic manifolds which have very nice complex structures, and then with some kind of compatibility condition. Again, maybe I'll mention it later. These are called Keller manifolds, and they are from the symplectic structure. In the complex structure, you can produce a metric, a very nice metric called a Keller metric. So this is a special class where many results are easier or more results are true than in the standard situation. And in particular, here there is a question about toric manifolds. So toric manifolds is an example, or whatever class, a huge class of Keller manifolds. And this example of Cn, here we would also have a standard Keller structure. This is not a compact, but this is a nice Keller manifold. So the complex structure of Cn, it talks nicely to the symplectic structure omega standard that we define, and you can produce a metric out of it, and this metric verifies the Keller condition. It might we'll see. Probably we'll talk about it later in the course. But that's true that that's a big interplay between complex geometry and symplectic geometry. Moreover, you know, there is a new field, or relatively new field of geometry started about 20 years ago, I would say, and it goes under the name of generalized complex structures. So they are people instead of the tangent bundle, because usually geometric structures, that's something about the tangent bundle. And they are people take a direct sum of a tangent and cotangent bundles. You get a bigger gadget and you start defining geometric structures there. And it's interesting that the notion of a generalized complex structure, it includes as particular examples, complex structures and symplectic structures. And this whole story to some extent is motivated by some even more advanced and mysterious story called mirror symmetry, where people relate complex and symplectic structures, that's these ideas from physics. So they relate them by some kind of we can say, generalized Fourier transform, this mirror map going from symplectic to complex structures and the other way around. So there are relations at many, many levels. I'm not at all a specialist in all of them, but at least I kind of, it's a very good question. And yeah, there are many, many answers to that question with varying degree of difficulty.
Thank you.
I'm sorry, I thought the question was about the other way. So is the complex manifold always symplectic? But the answer is no, and you present an example.
Yeah, I don't
think so. You have actually already presented an example at the beginning of the lecture. Actually.
Did I? Okay.
Yes, S1 cross S3 is an example of complex, which is not symplectic.
That's right.
How we prove that it's not symplectic?
Which one?
S1 times S3.
Oh, because it doesn't have the second homology. Its second homology group is 0.
Ah, of course, yeah. Like we can calculate it using Meyer-Vietor resources.
Well, I think maybe you kind of, we have a Punnett formula, right? And H2 of the circle is clearly 0 for dimensional reasons. And then for a sphere S3, sure, whatever, like from, yeah, H2 is 0, but there, yeah, you choose your favorite method, how you calculate it. So you need to know the homology of spheres, and real homology, right, of spheres, you kind of.
So it's like unit form for
the
Ramka homology, okay.
Yeah.
I suppose it doesn't have 2 cells, so its second homology is 0, and thus its second homology is 0 too.
Right. Okay, people, more questions?
I have a remark on minus signs.
Okay.
I found in McDuff's and Salmon's book a remark that so below you wrote well, the Hamiltonian equations, and if we want to put them in this form, then we first of all, well, could you show them the Hamiltonian equations there somewhere below?
Yeah, right.
Yeah, first of all, if we want to put them in this form, then we do need to have the minus sign in this formula with contraction, where we take the contraction of omega and it equals minus dh. And also, if we write it in coordinates, this is equivalent to writing our two form as dp times dq.
Oh yeah,
in this
right.
order.
Yeah, that's what I'm doing. My 2 form, I choose to have dp wedge dq, and then I need this minus sign to get the correct, or whatever, the standard form of Hamiltonian equations. Yeah, I think that's correct. Of course, this is a matter of choices. So one could have chosen the signs in a different way, but and probably later on I'm going to have some sign mistakes. You're very welcome to catch me and correct me.